Electromagnetism is the study of the relationship between electricity and magnetism. When an electric current flows through a wire, it generates a magnetic field around it. This simple principle forms the basis of electromagnets, devices that use electricity to create a temporary magnetic field. Unlike permanent magnets, which are always magnetic and retain their magnetism without needing any power, electromagnets only work when electricity flows through them. This means their magnetic field can be switched on or off and adjusted by changing the strength of the electric current or the number of wire turns in the coil. Electromagnets differ from permanent magnets in several ways. While permanent magnets are made from materials like iron, steel, or special alloys and always retain their magnetic properties, electromagnets are created by passing current through a coil of wire, often wrapped around a soft iron core. Their magnetism is temporary and controllable. This controllability makes electromagnets extremely useful in real-world applications. They are used in electric bells and buzzers, where the magnet pulls a striker to make sound. In motors and generators, electromagnets help convert electrical energy into mechanical energy and vice versa. They are also used in MRI machines in hospitals, in cranes at junkyards to lift scrap metal, in relays and electric switches for automation, and even in magnetic levitation (maglev) trains that float above tracks with no friction. A solenoid is a specific type of electromagnet made by coiling wire into a helix or spiral, often around a soft iron rod. When current flows through the wire, the solenoid produces a magnetic field similar to that of a bar magnet. The field lines inside the solenoid are straight and evenly spaced, indicating a strong and uniform magnetic field. While outside the solenoid, the field is weaker and curves outward, just like around a regular magnet. The two ends of the solenoid act as magnetic poles, one as a north pole and the other as a south pole. The strength of the magnetic field around a solenoid depends on the amount of electric current, the number of turns in the coil, and the presence of a core material like iron, which amplifies the field. This controllable and concentrated magnetic field makes solenoids very useful in devices that need precise and strong magnetic forces. Now that we understand how electricity can create magnetism, let's look at the opposite side of the story: how magnetism can create motion. When electricity flows through a wire placed in a magnetic field, the wire feels a push or force. This happens because the moving electric charges in the wire interact with the magnetic field. This force makes the wire move and is called the motor effect. It's the basic idea behind how electric motors work. To figure out which direction the wire will move, we use something called Fleming's left-hand rule. If you stretch your left hand with the forefinger pointing in the direction of the magnetic field, north to south, the middle finger in the direction of the current, positive to negative, then your thumb will point in the direction the wire moves. This rule helps us understand the working of electric motors. An electric motor changes electricity into motion. It has a coil of wire placed between the poles of a magnet. When current flows through the coil, it experiences a force and starts to spin. To keep it spinning in the same direction, the direction of current needs to flip every half turn. This is done using a split ring and brushes. The split ring switches the current's direction after every half turn, and the brushes help pass electricity to the spinning coil. This keeps the motor rotating smoothly. Now let's talk about the opposite, turning motion into electricity. This is called electromagnetic induction and was discovered by Faraday. He found that when a magnet is moved in and out of a coil of wire, electricity is produced in the coil. The electricity only flows when the magnet is moving. This showed that a moving magnetic field can create electric current. To find the direction of this current, we use Fleming's right-hand rule. If you stretch your right hand with the forefinger pointing in the direction of the magnetic field, the thumb in the direction of the movement of the wire, then the middle finger will point in the direction of the current. This rule is used in electric generators. An electric generator does the opposite of a motor. It changes motion into electricity. In a simple generator, a coil is rotated between two magnetic poles. As the coil turns, it cuts through magnetic field lines and electricity is produced. The ends of the coil are connected to rings and brushes help transfer the current to the outer circuit. There are two types of generators: AC, alternating current, and DC, direct current. In an AC generator, slip rings are used, and the direction of current changes every half turn. This produces alternating current, which goes back and forth. In a DC generator, split rings are used to keep the current flowing in the same direction. AC is used in homes and industries, while DC is used in batteries and small gadgets. So, electric motors and generators are just two sides of the same idea. One uses electricity to make movement, and the other uses movement to make electricity. Both are super important in our everyday lives. If you found this explanation helpful, don't forget to like, share, and subscribe for more simple science videos.